Okay, coding start, and I'm going to share the screen. Yes. Okay, cool. So lecture. So yesterday we talked about. Let's give you some recap. So yesterday I talked about the normal stress. I mean, purpose of the mechanics of materials, of course, and then we talk about uh, normal stress definition. Okay, stress definition is it needs to be in the middle part of the bar, okay? Otherwise, you will encounter a very complicated regions of the stress distribution. Okay, the stress distribution is really complicated at the tip of the bar. Okay, so when we actually going to explain the definition of the stress, we need to take the center part because the force just like a flow, just like a river. Okay, so you think it seems like it kind of inserting some the inhale of the water and then it spread out. Okay, and after some distance, it become the uniform flow. Okay, however, in this region, the water just came through in this hole, and then you can see that there's nothing filled. I think it will be dry if you pour down the water, right? It will be dry. So the dry things just analog, really similar to the condition of stress-free, sigma x equal to 0. Okay, and we talk about the normal strength is just the percentage of the elongation. And we done some examples, and compressive stress or compressive strain will be negative. Okay, and the typical number, typical value of the stress should be around in normal solid should be M par or G par. Okay, 10 to 6 or 10 to 9 PA, and the strain should be around 1%, 0.5%, such very small. If you calculate the strain like 12%, something wrong. Of course, there are still some materials which can have such high strain, 12%, 18%, and then still go back to its original shape. It will call super elasticity. Okay, but well, we will discuss this if you are in our lab. Okay, and then this part we talk about the self weight of the rod, and then we focus on the concept of this example is that if we want to see any point, examine the stress at any points, we just need to cut it. Okay, if we cut it and then we separate them into two parts, and the interface must have some load, some force on it. Otherwise, the other part cannot maintain equilibrium state. Okay, so if we cut that, we know that each part must follow equilibrium equation. So in order to maintain the equilibrium, we need to add some force, the force on it, and then we need to calculate that we know the internal force in that point, at that point. So if we cannot, so if we can calculate this, we can calculate the stress, just divide by its own area. So the area stress on that point will be calculated. Okay, so that's the most important concept in this example. And then we talk about why we are going to use strain and stress, because the strain stress belong to get rid of the geometry effect. We only have the material effect. Okay, and then this is a standard that we are going to use to measure the mechanical properties. And then this is the novel brush tensile test. I believe you saw some of the video like this. So okay, so when you have the tensile test on the bar and you see they kind of shrink it, you call necking, and then it will break eventually. Bam. Like a energy release. Okay, so energy release, and you can see the fracture cross section, right? 好啦，赶快加入你们。没有啊？为什么没有？啊，有，你啊是助教，谢谢你 ，Thank you。Right. So 对我刚刚想到，就是如果我先不把你加入的话，你也没办法加入。Okay, let's do it. Okay, so this is the tensile test. Wait. Okay. So now let's talk about the normal stress and normal strength, and true strength and true stress. So normal, nominal, not normal. Nominal means that the everyone calls that. Okay, so we also call this conventional. Conventional means that everyone thinks as a rule, so everyone obey that rule. Okay, so this is a nominal and conventional stress, or we call engineering stress. I mean, this engineering means doable, workable. Okay, it practical. Sometimes when you do the engineering, you just make it work, and then you don't need to fully understand that. So science, you need to fully understand that. But engineering means that it just work. It's okay. Okay. So engineering stress means that it's approximately okay, correct, but not really 100% correct. Okay. So it's easier for us human can accept that. Okay, so sigma E means engineering stress, and this is exactly we talked about yesterday. Okay, this is what we use normally. Okay, so the A area is actually the initial area, P divided by A0. A no. Oh, in English, which sometimes we will say zero means in no. A no. A O, well, A0, you can call this, but typically when you have a subscript, this is a subscript of the 0, you will say A no. No means that the initial, in the beginning, okay, before the loading or before anything else happened. So A no is initial area, P divided by A no, okay? So in the previous few example, we use A no, right? And a nominal strength, 工程应变, is that epsilon E equal to delta divided by L no. L no is initial gauge length, initial length, okay? So yeah, that's it. So this is the initial state of the bar. This is, we've done that before, we taught that before. However, actually, you can imagine that when you apply a loading on the bar, typically you apply that slowly, right? So you can like step 1, step 2, step 3, step 4. But actually, when you do that, your area will shrink. Right? Yeah, shrink, because you stretch that, the area will shrink. So typically, A will less than A no, right? This is acceptable, right? And also, when you do the step 1, step 2, step 3, actually the step 2, the original length of the step 2 will be L, which is longer than L0, L no, because L no is a step 1 original length. But when you do the step 2, the step 2 original shape will be the step 1's result, right? So you can imagine that actually, if you are talking about the true stress or true strain, the area keep changing during the stress loading, and the original length keep changing at each step, each small step. So the true stress is actually sigma T. The T means true, right? True equal to P divided A. The A is actual area, the area at that moment, So this is a little bit different. We talk about. Okay, so also the true strength or natural strength, true strength means that the epsilon T equal to delta L. The L should be at that moment, the L, the previous step, the resulting length of previous step will be your current original length. Okay, so this is a little bit tricky. So you can imagine that this is step 2, and then your original shape, original length has been increased a little bit compared to L no. Okay, so and then next step, the delta will be at that at that time, the true strength will be calculated. So imagine that when you have a bar. Okay, so the point here, actually is a measurement of the gauge. Gauge is kind of the small device that you can stick on the bar or stick on the material, and then you can measure strain gauge. You can measure the strain or measure the elongation on the material surface. Okay, so when you attach this gauge, the gauge will tell you L no. What is L no? And what is the L? Okay, so L plus delta, sorry, L plus delta. Okay, and then so you can imagine that the true strength will be the infinitesimal strength at each step, loading step, and then accumulate them together. Okay, so you need to do more like integration things. So you can imagine that this is sum of all the instantaneous strain. Okay, so each infinitesimal step strands need to be added up together, and then it will be your true strand. So epsilon T equal to the integration of each small strand. Okay, and the integration will be start from L0 to L final, right? No, and this D epsilon will be the small change of the length and the current length. Okay, so after that you will have natural log LF. I believe most of you passed the calculus in your first year, right? So suppose you can understand why the integration looks like that. One plus epsilon E. Okay, so true strength will be natural log natural log 1 plus epsilon x engineering strength. That's the relationship between nominal or engineering strength and true strength. Okay, but of course you can see that this is really complicated. We are not going to use that during our course, but I just going to tell you the definition of the engineering strength and stress and true stress and true strength. And then if you can see that, we can compare engineer and true stress and strength. Which one is greater? Which one is less? You can see that because the area will keep when we do the tensile stress, tensile test, when you stretch, elongate the bar, the area will keep shrinking. So A no greater than A, so the sigma T will has less number to divide by less number. So the sigma T will be greater, right? Greater than engineering stress. However, by contrast, the L, the original length for each step will always greater than the first step original length. So L greater than L no. So which means that epsilon engineering strength will always greater than epsilon true strength. Okay, so I guess that's the I explained this page. Do you need translation on that? 要不要？需要吗？需要。好，总之就是真实应力就是啊，真实应力就是在每一个状态下的 area 的面积，我们的分母都是要用真实的面积。OK， 那但是这很麻烦啊，你要没事去 track 它的面积，超难的。所以其实真实应力很难算啊，很难算。那工程应力的话，就是直接拿初始的面积来除就好了。那因为初始的面积比较大。因为如果假设是拉伸的状态下，初始面积比较大，所以说它的 engineering 的工程应力会小于工程真实应力，因为真实应力跟就是应力是除以它的面积嘛，对不对哈？所以这边会小于它，讲错了，对，sigma 1会小于 sigma t， 这个应该 OK。那工程应变真实应变什么意思呢？我们工程应变一样，就是拿最初的原本的长度来去除它，但是真实应变不是，真实应变是其实啊，说实在的，每一个步阶，我们不是说我们拉伸都是非常缓慢的吗？所以你可以把一个，例如说一个 deformation 这样拉过来，你可以其实要分成一点这样拉，但是你这样一点一点这样拉的时候，你在拉第一个阶段的时候的 strength 是它的原本的长度其实是会越来越长的啊。你的第一步是长这样子，第一步的时候长这样子，然后拉完以后，你的原本的长度就变长了。到第二步的时候，你再拉，你的原本的长度就变更长，它就会一直你的第一步跟第二步要分开来看，这样，所以它是把每一个小步的 strength 加总起来，才是你的真实应变。所以这就是为什么我们要用积分的方式，每一个小步骤的应变都要把它加起来，才是你的真实应变。但是工程应变就是随便拿哈，就直接就是直接一步到位这种感觉，所以它会少一点点东西啊，大概是这样的意思。好，那在拉伸的状况下的话，每一步阶的原本的长度都会越来越长，越来越长，越来越长。好，等于是一个重新的，每一个步阶都是重新的开始的感觉。那所以说你的 L 会大于你的 L0的话，那它是分母的话，你的工程应力，工程应变就会大于工程真实应变，大概是这样。好，希望这样子可以听得懂。OK，next，翻译完成。接下来呢，sorry，next I believe this figure you have seen this figure before because this also introduced by introduction of material science engineering. I believe you can you know that this curve start from here and The x-axis will be strain, and y-axis is sigma, is stress. So this is stress-strain curve or stress-strain diagram, okay? And the structural steel is a really typical materials that we can talk about. And the behavior of this material will be a really standard, really typical, okay? So let's start. So at the first, it behaves linearly, okay? So linear region, if you have certain times of strain, you will have certain times of stress. So they are proportional, 就是等比例啦，等比例 proportional. But this is not really always the case, right? So it will exceed the proportional limit. So it will, at that point, they are not linear anymore. They become a little bit curve. And then after the proportional limit, it will soon arrive yield stress, which means that the yield stress means that they are not elastic anymore. What is elastic? Elastic means that it will go back to, after your unloading, it will go back to the original shape. But after the yield stress, which means that you are destroying or some defect occurred in the inside the material. So it starts to it called yield. What is yield? Yield. I yield. I start to fight. Okay. I lay down, become lazy. Okay. I yield. Okay. So which means that stress won't, they won't have any more stress to against the strength. So the strength will suddenly increase. Okay. And then it's called perfect plasticity or yielding. Okay. And oh, by the way, sorry, I forgot to tell you, mention that the linear region for general purpose, what does that mean? For your general usage. Okay. For example, you are expecting your chair is in this region, right? So lighter person sit down and it will deform a bit, and heavier students sit down that it will deform more. But you don't expect it when you sit on that, it change a lot of strength, right? So it won't use, it's not usable if you put the weight and then you have bunch of strength that won't be usable, right? So typically we use that region. All the material you are using, we typically focus on this region. Okay. So now let's go back to the yield stress. The material yield, they just refused, give up. They just give up. Okay, the material give up. So they have a lot of strain occur. But at some point, the material found that we cannot do that anymore. I still need to fight. So it kind of changed its microstructure. Okay, so maybe they have many other other way to change its crystal orientation to make it again, right? Try to against the strength. So it will become like this. Okay, so it will change its microstructure to make it to make the stress become higher. Okay, and then but still, if the tensile test still undergoing, it will reach a limit called ultimate stress, which means that it cannot afford anymore. Okay, and then it will fracture. Okay, and you can imagine that the necking happened, right? The necking in the video. So during that necking process, the strain will start to change. Strain will suddenly increase, but the stress will be decreased. So it cannot afford longer, no more. So it cannot afford the against stress, and then it will shrink, the necking shrink. Then it fractured. Boom. Okay, so this is actually the stress strain curve of that video. Right. So this red line is the curve of nominal stress or engineering stress. So original A0 is used. However, if you are using every step stress, okay, every step, if curve of true stress, you use the area at each point, and then you will find that after the elongation, you notice that the area, cross-section area shrink dramatically, right? So if we use the current area, cross-section area, the line should actually become higher. As you can imagine that, especially for this range, the area is shrink. So which means that the stress has divided by less value. So you will have higher value of the true stress. Okay? 这样子可以听懂吗? Can you understand that? Do I need to translate that? I believe all of you know that figure before. So, right, that's it. Oh, by the way, this is not to scale, okay? Typically this, this part is quite big. This part is quite small. The reason why they look like similar because this is only for illustration purpose. 示意而已, okay? Illustration purpose. So the real scale, it will be on the next page. The real scale looks like this. Oh, not bad. Yeah, this is a real scale. Okay. So ductile materials, typically metal, are ductile, and before the failure, they will typically have large permanent deformation. As I mentioned before, when you exceed the yield stress point, it becomes entering plasticity region. The plasticity region means that if you unloading, it will never going back to its original shape. Okay, so ductile material means that before it break, it will has a lot of region of plasticity. This region is plasticity region. So if you at that point you unloading, you will have permanent strain, 永久的 strain. It never recover. Okay, before it break. If you go to this point and then you unloading, you will have the permanent strain. Okay, for example, aluminum, copper, they will all have this kind of behavior. But the brittle material means that they don't have, they typically has less region of plasticity. So after the proportional limit A, and then it break really quickly. Okay, so you can see it has less permanent strain. If it unloading, you will have smaller permanent strain. Okay, so for example, the glass or high carbon steels. Okay, understand what I'm talking about, right? Introduction of material science engineering. I believe you have really good teachers for you to teach this. So I don't need to spend too much time on it. Right, so stress strain diagram. If we don't have the, sorry, I should draw it. Okay, so if it doesn't have a very obvious yield stress platform, if we don't have that, how can we define the yielding stress? So for example, if you are a material producer company, if you are selling a material, and in your material explanation, you need to give the detailed information for your product, right? So when you selling a product that has no obvious yielding stress platform, how can we write down the yield stress? We still need to give you a number, right? Otherwise, the buyer won't know the property of that material. So typically, we will using the method of shifting. Okay, shifting method. The shifting method is that if you have you always have the elastic curve, right? Elastic part, the linear elastic region, and you shift that slope by 0.002. Don't ask me why 0.002. I don't know why, but this is a conventional. Okay, everyone agree with that. So after you shift 0.002 offset, and then the point, the point here, we will say, okay, this is sigma yielding stress. Okay. Well, I don't know why they use 0.002, but this is the way. If they don't have the platform, we use that. Okay. And also we said the stress strain curve for material under compression and tension are not similar. Okay, not the same. Okay, so typically the under compression, the curve will looks like the okay. Okay, so it won't looks like the previous one, the platform and then necking and then strengthening. This is previously this tensile. But for the compression, it will looks like another different story. Okay, and of course we know that after the compression, the cross section of area will be increased. Okay, I don't need to explain that, right? I don't need to translate that, right? Now, after that, we are going to talk about loading and unloading. Loading and unloading. So when the stress and strain curve return to the original point O along the original curve after unloading, which means that the material exhibits elasticity. They are in the elasticity region. Okay, so you can see that it loading, unloading. Okay, so in the same curve. So this is elasticity. And there's a limit, E, okay? After the elastic limit, E, so it could be proportional limit or it could be yielding stress point. Or as long as passing that point, it cannot going back to their original shape and along the same loop, the same path, it will pass the elastic limit. Okay, so if you pass the elastic limit, so after this point, they are not elastic anymore. So permanent strength or residual strength will be occurred. Okay, so for example, if your loading reach to the point B, the B is exceed the E point, the elastic limit. So if you unloading, which path it will go? It will follow the initial slope. They will going back to, well, sorry, it will going back to this. Follow. These two lines will parallel. Okay, they will follow typically they will follow the first slope and go back to its stress-free state, but they still have residual strength or permanent strength. Okay, and of course this one is still a little bit elastic recovery, but it cannot recover to the original shape. Okay, of course, if you go to this point, yes, it will still follow this line. Okay, so imagine that you loading, unloading, loading, unloading, loading, unloading, loading, unloading, oh, loading here, loading here, loading here, loading here. So you can imagine that it starts to retreat. The plasticity region is start to retreat, and you gain more and more residual strength. Okay, that's it. 需要翻译吗？不用吧，这蛮简单的。Okay, so let's talk more about the plasticity. So the plasticity means that you change the material. You have changed the material structure inside. So, sorry, I need to draw that again. Do you know the reason why I need to draw that again? Because I cannot use the figure directly from the textbook because the author plotted, not me plotted, so I cannot reuse them. Otherwise, I will the copyright, right? So I need to draw them by myself. Well, sorry, teaching assistant. Anyway, so when the material exceeds its elastic limit, the behavior changes dramatically. Of course, you see, they're changed. And it's called plasticity region. And in most cases, the new elasticity limit point B will be higher than the original one. This is actually, I explained this in the previous page. I said loading, unloading, loading, unloading, loading, unloading. But after the elastic limit E, it will start go back to here, loading, unloading to here, unloading here, and then if you loading again, exceed that, it will come back to a new point. And then you loading again, and you will go back to the original, go back to the path, and then unloading. Okay, so as we mentioned before, this darker blue region is called plasticity region. It's retreat, retreat, retreat. And then while you're retreating that, your residual strength getting more and more, higher and higher, greater than greater. Okay, so that's it. Another thing I need to explain is that creep. Okay, creep. The creep is that the after long-term effect, time effect. Okay, with long-term fixed loads, the elongation will increase over time. Okay, for example, if you just hang a bar on the ceiling, just like that one, okay, the light, uh, these, I believe those bar is longer than I firstly came into this classroom. Okay, because 10 years passed, the bar will be longer. Okay, so this extra additional strength will occur. For example, the curve will be after through the time. The time zero means that after it fix it on the ceiling, it reached to this is called delta zero. So the first day of that bar hanging on the ceiling, it reached this point. And then after time, 1 year, 2 years, 3 years, 10 years, you start getting longer and longer, and eventually saturate. Okay, this is one of form of creep. The other form of creep is material relaxation. For example, I believe you typically use your 晒衣绳要怎么讲？A bar, hang your wet clothes, right? You dry your clothes, and then you have a bar fixed between the wall. Okay, so there's a wire, and you fix it with really tension foam. But after some time, it will become ding, 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 ding. Okay, because the stress on it will not so when you fix your wire between the wall and reach this point, and through the time, the stress will, okay, so that's it. Oh, and also the creep is effect. The creep is a kind of a high temperature effect. If you have higher temperature, the creeps will affect more significantly. Okay, you can imagine that because of the higher temperature, your atoms in the material will shake, harder, right? So when you do that, and it will release the stress even more. Okay. Now, next, I will talk about the Hooke's law. I believe you understand this during your senior high school. Okay, linear elasticity. Oh, Hooke's law is applied for linear elasticity. Okay, linear elasticity. The one unloading, unloading. This is not linear. This is elasticity, but not linear elasticity because this is not linear, right? This is curved. So Hooke's law only apply for linear elasticity. It's like a straight line rather than curved line. Okay, and sigma equal to E epsilon. Sigma stress. E is elasticity modulus. Young's modulus. Maybe the first one invented this named Young. Okay, I don't know. So E is a really important things. And you can imagine that because this is no unit. So the unit of E must be equal to sigmas. So it's pa. Okay, so today I will finish this course now. Okay, if you have any questions, just come to me and I will upload all the materials today. Thank you very much.